Welcome to Sotantra education. In this lecture, we are going to discuss the concept of AVL tree. So, before moving to the details of AVL tree, let us recall the concept of binary search tree. So, we have previously discussed about the concept of binary search tree. So, let us consider a binary search tree like this. So, we have one node 8, another one is 12. So, that is on the right subtree of 8, then the next one or the right child of 12 is 14, then the next node is 18, then assume it is 20, then assume it is 23, then 44, then assume the next node is 52. So, here you can observe this is a binary search tree, because here the root node is 8 and the next node is 12, that is greater than 8. So, 12 lies in the right subtree of 8. So, like this it is continued, or like this it continues. So, it is a binary search tree. So, here if we want to search the item 12, so whether 12 is present in this list or not. So, here to find 12 or to locate 12, we need two search operations, or to find 12 it needs two comparisons. Similarly, it takes 3 comparisons to locate 14. So, first we check, or first we compare with 8, then we compare with 12, then we compare with the next one, that is 14. So, after 3 comparisons we can say that 14 is there and its location this one, like this. Similarly, to locate 52, it requires 8 tests or 8 comparisons. So, this one is 1, 2, 3, 4, 5, 6, 7, 8. So, 8 comparisons required to locate 52, or we can say, if we generalize, the number of comparison is order of n for n elements. So, if there are n number of elements, so the total number of comparison is order of n. So, it is equivalent to a linear list. It is equivalent to a linear list. So, instead of this binary search tree, if we use linked list, if we use array, then also the order of comparisons to locate one element is order of n. Then why should we go for binary search tree, or what are the limitations here? So, the limitations in this binary search tree is that this particular binary search tree is not balanced. That is why the number of comparisons is order of n. So, while the binary search tree is simple and easy to understand, it has the major problem, that is not balanced. So, binary search tree is not a balanced tree. So, we can write that one, that binary search tree, instead I am writing BST, is not a, or is not balanced, is not balanced. So, this is the major limitation of binary search tree. To deal with this limitation, in 1962, two Russian mathematicians named as G.M. Adelson-Velsky, Adelson, Adelson, VLSKII. So, Adelson-Velsky, and another one is E.M. Landis. So, these two Russian mathematicians created a balanced binary tree structure, or balanced binary search tree structure, that is named after these two mathematicians. That is, the name of the tree is AVL tree. So, this A and B comes from here, Adelson-Velsky, and L comes from here. So, the two mathematicians developed one balanced binary search tree, and that balanced binary search tree is AVL tree. So, we can say an AVL tree is a binary search tree in which the heights of the subtrees differ by no more than 1. So, in AVL tree, the difference between the height of left subtree and right subtree is not more than 1, or we can say like this, or we can write the same thing. So, in AVL tree, the heights of the left subtree and right subtree differ by no more than 1. So, in an AVL tree, the height of left subtree minus the height of right subtree. So, we can write like this: height of left subtree minus height of right subtree. So, this value will be -1 or 0 or +1. So, it is maximum 1. So, the height of left subtree minus height of right subtree will be -1, 0, 1. That means the height is going to differ by at max 1 or at most 1. So, consider some examples. So, let us consider here one node is 4, then 6, then 2, then 3, here it is 7. Now, consider this one: is it an AVL tree or not? So, here you can consider for node 7, what is the height of its left subtree? It is 0. Here no left subtree there, so height of left subtree is 0. Then what is the height of right subtree? Here it is also 0. So, for 7, the height of left subtree minus the height of right subtree is 0. Now, for 6, so for 6, what is the height of left subtree? It is 0, because no left subtree is there for node 6. What is the height of right subtree? So, it has only one node, that is 7. So, height of right subtree is 1. So, 0 minus 1, it is -1. That means height of left subtree minus height of right subtree. So, that is equal to 0 minus 1. So, 0 minus 1, it is equal to 0, sorry, -1. So, 0 minus 1, it is equal to -1. Now, consider node 4. So, here what is the height of left subtree? So, the height of left subtree is 2. What is the height of right subtree? So, right subtree is also height 2, because this one you can consider. So, height of left subtree, height of right subtree, if we subtract, so it will be 0. Now, consider this one node 3. So, for node 3, what is the height of left subtree, what is the height of right subtree? So, it has no left subtree, no right subtree. So, the difference is 0. Now, for node 2, it is -1. Height of left subtree is 0, height of right subtree is 1. So, 0 minus 1, it is equal to -1, equal to -1. So, here you can observe all the difference of left subtree minus right subtree is maximum 1. So, we can say this one is an AVL tree, and this value we can write like this: height of left subtree minus height of right subtree is nothing but balance factor. So, these values like 0, -1, 0, -1, 0, these are the balance factor. So, the balance factor of a node in an AVL tree is nothing but the difference of left subtree, the difference of height of left subtree minus height of right subtree. So, for an AVL tree, the balance factor will be 0 or -1 or +1. So, in an AVL tree, the balance factor of the nodes will be 0, -1 or +1. So, there are only 3 values here, no other values are allowed. Now, consider another example. We have one node 4 another one is 6, another one is 2 here left child, for 6 it is 5, right it is 7, for 7 it is right 9. So consider this one, it is also a binary search tree. Now find the balance factor. So here balance factor will be 0, here it will be -1, here it will be 0, here it will be 1 minus 2, that is -1, here it will be 0, here 1 minus 3, so it is equal to -2. So the balance factor of node 4 is -2. So we can say this tree is not an AVL tree. So this one is not an AVL tree, because here for node 4 the balance factor is -2, but in an AVL tree the balance factor will be -1 or 0 or +1. So as here in this example the balance factor of the root node 4 is -2, then we can say this tree is not an AVL tree. Now consider some other example. So here we can take like 45, then 63, then 36, then assume it is 27, then assume it is 39, here it is 54, here it is 72, here it is 70. So this is a binary search tree, because we know that each AVL tree is a binary search tree. So now we will check whether this binary search tree is an AVL tree or not. So first find the balance factors for each node. So it is 0, it is 1. For 72 the balance factor will be 1, that means the height of left subtree is 1, the height of right subtree is 0, because it has no right subtree. So here it is 0, here it is -1, the balance factor will be 0 here, here it will be -1, here it is 0, here it is 0. So here also 1 minus 1 0. So here it is 2 minus 3, it is equal to -1. So 2 means the height of left subtree is 2 here, and the height of right subtree this one 3. Height means the maximum path length from root to the leaf. So here 1 2 3, so that's why we have written 3, the height of right subtree. So it will be 2 minus 3, that is -1. So here you can observe for all the nodes the height of left subtree minus the height of right subtree, or we can say for all the nodes the balance factor will be 0, 1 and -1. So this one is an AVL tree. Now consider another example. So let us delete the balance factor, or let us take another example. Consider 8, then 4, then 10, 9, 11, then 12, then it is 2, here it is 6. Now find the balance factor of each node. So here it is 0, 0, 0, here it is 0, 0, it is -1. So for 10 it is 1, -2, -1. So for 8 1, 2, minus 1, 2, 3. So 2 minus 3, so it will be -1. So we can say this tree is an AVL tree. Now consider, I am updating this binary search tree only, assume this one. So now here update the balance factor. So for 9 it will be 0, or for 12 it will be 0, for 11 it will be -1, for 10 it will be -1, for 8 so it will be 1 minus 1, 2, 3. So 1 minus 3, that is equal to -2. So here it violates the condition for AVL tree. That's why we can say this tree or this binary search tree is not an AVL tree. So this one is not an AVL tree. So I hope the concept of AVL tree is clear. Now let us take some more examples. So assume the month names are sorted following the alphabetical order. So here in the root it is May, then March, then August, then April. So following the alphabetical order, this binary search tree is constructed. Now find the balance factor. So it will be 0. So for April it will be 0. For August it will be +1. For March it will be +2. For November it will be 0. For May it will be +2. So here you can observe for March and for May the balance factor is 2 and 2. So that's why this structure is not an AVL tree, or this binary search tree is not an AVL tree. Now consider another example. Suppose it is 45, 63, 36, 72, it is 54, then in the right it is 89. Now find the balance factor. So for 89 the balance factor will be 0. For 72 it will be -1. For 63 it will be 1 minus 2, so -1. For 54 it will be 0. For 36 it will be 0. For 45 it is 1 minus 1, 2, 3. So 1 minus 3, so it will be -2. So for 45 the balance factor is -2. That's why we can say this binary search tree is not an AVL tree. So all binary search tree are not AVL tree. So the balanced binary search tree, that means the binary search tree in which the difference of left subtree, the difference of height of left subtree and the height of right subtree is at max 1, that binary search tree is called as AVL tree. So I hope the concept of AVL tree is clear. So we can say an AVL tree, so let me write this thing, an AVL tree is a height balanced binary search tree. So an AVL tree is a height balanced binary search tree. Now consider one height balanced binary search tree or one AVL tree. So like this. So at the root it is 23, 18, 44, 12, 20. So it is 8, it is 14, it is 52. So now here in this tree structure, if we want to locate node 8, so whether 8 is present or not here, if we want to find whether 8 is present in this list or not. So to find 8 we need to start from the root. So first compare 8 with 23. So is it matching? No. Then 8 is less than 23. So search in the left subtree. Search in the left subtree because it is a binary search tree. So here one comparison. Then compare 8 with 18, so 2 comparison. Then 8 is less than 18, then move to node 12, so 3 comparison. Then 8 is less than 12, so come to here, come to the left subtree, so 4 comparison. So to locate or to find whether 8 is present in this binary search tree or not, we need 4 number of comparisons. Similarly, if we want to find whether 14 is present in this list or not, so how many comparisons required? So 4 comparisons required. To check whether 14 is present in this list or not, we need 4 comparisons. Similarly, if we want to check whether 20 is present in this list, so we need how many comparisons? So to find 20 is present in this list or not, we need 3 comparisons. Similarly, for 52 we need 3 comparisons. So to check whether 52 is present in this list or not, so first compare 52 with 23. So 52 is greater than 23, so move to the right. Compare 52 with 44, so 52 is greater than 44, move to the right. So 52 is equal to 52, so we can say 52 is present in this list. So if we follow this path, so how many total number of comparisons we perform to find 52? So 3 comparisons. That's why we have written 3 here. So here you can observe the maximum search effort for this tree is either 3 or 4, or you can say the maximum is 4, so not 3. So the maximum search effort or the maximum number of comparisons to find one element is present in this list or not is 4. Or if we want to generalize, so in this structure, if we want to generalize, if there are n nodes, then what is the number of comparisons? It will be order of log n. But previously here you can observe, here what is the number of comparisons? It is order of n, but here it is order of log n. Why order of log n? Because this binary search tree is a balanced one, and here you can observe this binary search tree is not balanced. So now you can find or you can understand the importance of balanced binary search tree or the importance of AVL tree. Why we are discussing the balanced binary search tree? Now assume there are 1000 nodes. So assume there are 1000 nodes or 1000 records in a binary search tree, and if the binary search tree is not balanced, that means in this way, if it is right skewed tree, so this type of binary search tree are called as right skewed binary tree. So if the binary search tree structure is like this and assume 1000 nodes are there, so the number of comparisons to find whether one element is present or not is order of n, or we can say it is 1000. Now if the tree is balanced like this, so if the tree is balanced like this, then what is the number of comparisons? So it is order of log n, or we can say it is approximately 10 to find whether one element is present or not. So for 1000 nodes, if the tree is balanced, the maximum number of comparisons is 10 to find whether one element is present in this tree or not. And if the binary search tree is not balanced and it has 1000 nodes, then at max we can say the number of comparisons to find one element is present or not is 1000. So compare, here it is 1000, here it is 10 for balanced. So that's why we are reading the balanced binary search tree, or here in particular AVL tree. Now we will discuss the operations on AVL tree. So let me write this thing: operations on AVL tree or trees. So what are the operations that can be performed on AVL tree? So first one is searching, then insertion. We can insert a node into an existing AVL tree. Then we can also delete a node from an existing AVL tree. So the searching is performed exactly the same way as it is performed in a binary search tree. So it is exactly same as the binary search tree. So first search, compare the value that we want to search with the root, then if the value is smaller, come to the left subtree. If the value that we want to search is larger than the root, come to the right subtree. Like that, it is exactly same as binary search tree. And here in AVL tree, as the tree is balanced, so here it requires order of log n time for the search operation, because here the tree is balanced. Now move to the insertion. So the insertion here is of two steps. So the first one is insert following the principle of binary search tree, then insert in the same way as it is done in BST. So insert in the same way as it is done in BST. And in second step, whenever we insert a node into an existing AVL tree, so the balance factor may be hampered, or we can say the resulting tree may be unbalanced. So when we detect that a tree has become unbalanced after the insertion of a node, we must rebalance the tree. So AVL trees are balanced by rotating the nodes to left or right. So after insertion, if the tree becomes unbalanced, then apply rotations and make the tree balanced. Then the next one is deletion. So here also deletion is exactly same way as it is in the binary search tree. So delete following the same principle. You can write same principle as in binary search tree. And after deletion, if the tree become unbalanced, then perform some rotations to balance the tree. Now we will see some examples of how we can perform the insertion, how we perform the deletion, how we perform the rotations. So first come to the example, that is insertion, because we are not discussing the searching operation, because searching we have already covered in the binary search tree. We have taken a lot of examples, and if you have not seen the videos of how we can perform the insertion operation in binary search tree, please visit the video. We have video lecture we have already discussed. So now come to the insertion. So assume the binary tree is like this. So 5 is at the root, then it left child is 2, right one is 8, then it is 1, it is 4, it is 7. So assume this is the given AVL tree. So this is the given AVL tree. Now we want to insert. Okay, so here we can also consider another one 3. Now we want to insert another node 6 into this binary search tree. So if we want to insert 6, where 6 is to be inserted following the principle of binary search tree insertion. So first compare this 6 with the root. So 6 is higher, then come to the right subtree. So 8 is the root, new root, and 6 we want to insert. So 6 is smaller, so come to the left subtree of 8. So we reach 7. Then 7, compare 7 with 6. So 7 is higher, So come to the left of 7. So here the left subtree of 7 is empty. So here we create a node and insert 6. So here you can observe after insertion what will be the balance factor. So for 6 it is 0, it is 1, then it is 2. Now here you can observe for node 8 the balance factor is changed and it becomes 2, and 2 is not allowed as a balance factor in an AVL tree. Now we want to perform rotation in this AVL tree and we need to make this a balanced one. So how to perform rotation? So here which one is the critical node? The critical node is 8 because its balance factor is 2. Now move towards the newly inserted node from the critical node. So if we move towards the newly inserted node, the path is like this. So from 8 move towards left, and from 7 again move towards left. So if we move from the critical node towards the newly inserted node, then the path is like L or left. Now move just one step from the critical node, that is here we reach 7. Now assume that this tree is flexible, and if we pull this node 7 towards its left, then assume the gravity is doing its work and the tree is flexible. So if we pull 7 towards this, then this one 8 comes to here. So assume this is flexible, the tree is flexible and the gravity is doing its work here. So if we pull 7 here in this direction, then the node 8 comes downward. So the new structure becomes like this. So if we pull 7 here, then 7 becomes the root and 6 was already there, and 8 comes to the right of 7. Add this structure to the other part of the tree. So here you can observe. So it was 5, then 2, then 1, then 4, then 3. Now to the right of 5 it is 7, then 6, then 8. So here you can observe the balance factor will be -1, 0 and 1. So here in this tree we can say this tree is a balanced one and this is an AVL tree. So what are the rotation here we perform to make this one unbalanced tree to a balanced tree is LL rotation. So here we apply LL rotation and we get this balanced tree. So the rotation here we can term it is LL rotation. So after applying LL rotation to this tree, we get this one. So we will see some more examples. So assume the AVL tree is like this, 3, 2. So this is the AVL tree and it is balanced. So its balance factor is 0, it is 1, so it is balanced. Now if we want to add 1 to this tree, so we want to add 1. So where to add 1? So first compare 1 with 3, so 1 is smaller, then move to the left subtree, then compare 1 with this 2, so 1 is smaller, then move to the left subtree. Here you can observe the left subtree of 2 is empty, so create a node and create a node 1 and make this to the and make it to the left child of 2. So here now the updated balance factor it is 0, it is 1, it is 2. So here you can observe the balance factor of 3 is 2, so that is not allowed in the AVL tree. So for this we have to rebalance this tree by applying some rotation. So Which one is the critical node? The critical node is 3 because its balance factor is 2. Now from 3 or from the critical node move towards the newly inserted node. So this is the path. So if from the critical node, if we move towards the newly inserted node, the path is LL or left left. So we have already discussed about the LL rotation. So from the critical node just move one step or move to the next node and pull this one to its left. So if we pull this node 2 towards left or in this direction, then the gravity is going to play its role and 3 comes this side. So the new structure will be like this, 2 becomes the root and here it is 1, here it is 3. So if we apply LL rotation to this unbalanced tree, we get this structure, and here you can observe this is a balanced one. So this is an AVL tree, and here the balance factor will be 0, here it is 0, here it is also 0. So this one is a balanced tree, or we can say it is an AVL tree. So here also we perform LL rotation. Now we will see some more examples. So assume the AVL tree is like 20, then 18. So it is an AVL tree because it is balanced. Its balance factor is 0. It is it is plus 1. Now if we add 12 to this tree, so 12 is compared with 20, 12 is smaller, then move to its left. So compare 12 with this 18, 12 is smaller, then move to the left. So create a node 12 and make it the left child of 18. Now after insertion, find the balance factor. So it is 0. So for 18, so the balance factor will be 1. For 20, the balance factor will be 2. So height of left subtree minus height of right subtree. So here you can observe for 20, height of left subtree is 2 and height of right subtree is 0 because no right subtree is here for 20. So here you can observe, if we insert 12 to this AVL tree, the 20 becomes the critical node, or after insertion of 12, the AVL tree loses the property of AVLness, or we can say the tree becomes unbalanced. Now we have to balance it. So from the critical node, if we move towards the newly inserted node, so what is the path? The path is LL. So here we need to perform the LL rotation. So for that, move 18 or pull 18 towards in this direction. So if we pull 18 in this direction, 20 comes downside due to the gravity. So the new structure becomes like this, 18 becomes the root and 12 comes here, 20 comes here. Now this one you can observe, this one is a balanced one. So here its balance factor is 0, it's 0, it's also 0. So if we apply LL rotation to this structure, we will get this one. Or if we insert 12 to this balanced AVL tree, we get this one. So after inserting 12 to this structure, the new structure will become like this. Now consider some other example. So here assume that it is 18, the root, then left is 12, right is 20, here it is 18, here it is 14, then here assume, okay, so this is the AVL tree. So find the balance factor. So the balance factor here it is 0, 0, 0, here it is also 0, here it is 1. Now if you want to insert 4 here, so where 4 is to be inserted, so 4 is less than 18, so come here, 4 is less than 12, so come here, 4 is less than 8, so 4 is inserted here. So following the principle of binary search tree, 4 is inserted here. Now after insertion, find the balance factor of each node. So the balance factor here it will be 0, here for 8 it will be 1, for 14 it will be 0, for 12 it will be the 1, for 20 it is 0, no change, for 18 it becomes 2. Now here you can observe, after insertion of 4, the node 18 becomes the critical node. So from the critical node move towards the newly inserted node. So if we move towards the newly inserted node, then the path is like this. So move towards left, move towards left. So to make this all unbalanced tree to a balanced one, we need to perform LL rotation here. So how to perform LL rotation? So from the critical node, just move to the left subtree of the critical node and pull the node in this direction. So pull the node 12 in this direction. So if we move or if we pull 12, due to the gravity, this one comes in this side, this 18 comes in this side. So if 18 and if this part comes here due to the gravity and it pushes 14 here, 14 will be pushed like this, or 14, so let me draw the figure. So 12, the left is 8, 4 like this. Now if we pull for 12 here in this direction, due to the gravity this part comes here, or like this we can say 18, 20. Now when 18, 20 this part comes here due to the gravity, so it pushes 14 towards it in this direction. So this node 14 comes to the left of this one, this part. So 14 comes to the left of this part, or we can say 14 is placed to the left of 18. So if we apply LL rotation here, we are going to get the structure like this. So here you can find the balance vector. So it will be 0 here, it is 1, it is 0, 0, 0, it is also 0. So here this one is an AVL tree. So if we want to insert 4 to this existing AVL tree, first insert 4 following the principle of binary search tree, then apply LL rotation, and we are going to get the structure like this. We are going to get the structure like this. So after insertion of 4, the structure will become like this. So here we are going to execute LL rotation. So now we will see some more examples on this. So consider an existing AVL tree like this. It is 8, then 5, then 10, 3, 6, 9, 11, so it is 1, it is 4. So consider this is an existing AVL tree. So you can find the balance vector also for each node. It is 0, 0, 0, 0, 1, 0, 0, 0, it is 1. So it is an AVL tree because the balance vectors are either 0 or 1. Now we want to insert 2 to this node. We want to insert 2 to this tree. Now where we need to insert 2? So if we want to insert 2, first compare it with 8, then 2 is smaller, so come to the left subtree. So here we encounter 5, so 2 is smaller, come to the left. So here it is 3, 2 is smaller, come to the left. So here we encounter 1, so 2 is larger than 1, so move to the right. So here no right subtree of 1 is there, so create a node and insert 2 here. So when we insert 2 here, what is the updated balance vector? So the updated balance vector, here it is 0, here it is -1, here it is 1, here it is 1, 2, 3, -1, it is 2. So for node 8, here it is 1, 2, 3, 4, -2, so it is also 2. So here both node 8 and 5 have balance vector 2. So both are unbalanced node. So in this example
which one will be the critical node. So to find the critical node, move towards root from the newly inserted node 2, and first we find the unbalanced node 5. So here in this scenario 5 is the critical node.
So from this critical node move towards the newly inserted node. So the path is LL. So here you can observe the path is L or left. So 5 is the critical node. Then if we move from 5 towards the inserted node 2, so the path is LL. So what is the LL rotation? So just come to the left subtree of critical node and pull this one in this direction. So if we pull this one in this direction, then due to the role of gravity, this comes here, this part comes here, and when this part comes here, it has already one existing right subtree, so it pushes this right subtree, existing right subtree here in this direction. So when we pull this one in this direction, this part becomes the right subtree of 3 and the existing right subtree of 3 will be pushed to left. So let me draw the figure here. So I am drawing only the partial figure, only this part only, by considering this part. So if we pull 3 in this direction, so the structure will be like this: 3, then left is 1, right 2, then 5, then right of 5 is 6. Now this 4 is moved in this direction, that means towards the left of this part. So 4 will be added here. So after applying rotation, LL rotation here, we are going to get this structure. Now just add this one to the existing binary search tree. So how to add? So or connect this one to the existing. So it is 8, then 10, then it is 9, it is 11. So we are just connecting the updated path with the existing one. Now find the balance vector once again for each node. So it is 0, it is -1, it is 0, 0, 0, it is also 0, here 0, 0, 0. So for 8, 1, 2, 3, 1, 2. So 3 minus 2, it is 1. So here you can observe the balance vectors are 1, 0 and -1. So it is an AVL tree, we can say. So if we insert 2 here, then we need to perform LL rotation and we are going to get the structure like this. Now consider one more example. So consider the given tree is like this. So here the node is 45, then 36, then 63, 27, 39. So this is the given AVL tree. Here you can find the balance vector of each node. So here the balance vector will be 0, 0, 0, 0, it is 1. Now if we want to insert 18 into this existing AVL tree, so where we need to insert 18? So if we insert 18, so 18 is going to be inserted here only. So if we insert 18, after insertion find the balance vector. So it is 0, it is 1, it will be 0, so it becomes 1, it is 0 for 63, no change. For 45 it becomes 2. Now here you can observe after insertion for node 45 or for the root node, the balance vector becomes 2 and it becomes the critical node, because from the newly inserted node move towards root to find the critical node. So if from the newly inserted node, that is 18, if we move towards the root, we reach 45, which is the critical node. From the critical node again move towards the newly inserted node. So here the path is like this: left, then left, or we need to perform LL rotation here. So how to perform LL rotation? So just pull the node, that is left subtree of the critical node. So pull this one 36. So if we pull 36 in this direction, then this part comes here due to the gravitational force or due to the gravity. Now 39 is already one right subtree or right child of 36. So 39 comes here or pushed here. So let me draw the new structure. So 36, then 27, then 18, then 45, 63, and 39 is pushed to the left of 45. So 39 comes here. So if we apply LL rotation to this tree, then the structure will be like this. So here you can find the balance factors, and it is a balanced AVL tree, or we can say it is an AVL tree. So we have discussed the examples on LL rotation. How to perform LL rotation, we have discussed some examples. So in the next lecture, we are going to discuss how to perform RR rotation, how to perform LR rotation, and how to perform RL rotation. That means right, left, and right, left rotation.